Hello everyone. In this video, we're going to go ahead and finish up what we left off on Wednesday. I'll have another video for the new material. But remember when we were working on Wednesday that we had our variable here, our outcome. We were looking at sleep hours and wanted to know if we could find some predictors of it. So we looked at what was it, social work, credit hours, study hours, and then work hours to see if any of those particular variables, those predictors predicted our outcome of sleep hours. And in the process, we wanted to look at several of our diagnostics to see how well we were doing with the model. So I'll finish up with that here today. So if you remember correctly, and I'll pull up the table here. If you remember, we had that first model here, and we went through and we looked at the different diagnostics, including the model information. And so we had four predictors. One of them appeared to be significant in our output. We looked at our R-squared value. About 17% of the variance in our SLEP was accounted for by our predictors. We then looked at our residual descriptives and found that we were meeting our assumption there. We then looked at the probability plot, normal probability plot, and said that looked pretty normal, looked pretty good. When we looked at the histogram, though, we saw that there was a positive skew. We then looked at the residual plot, and we said it looked like there was about two unusual observations, and no symmetry, no equal variance, no linearity when it came to the residual plot. So it doesn't look like the diagnostics as far as those assumptions are looking very good for this particular model. Hopefully we can improve it a little bit. I think that when it comes to that symmetry, remember that symmetry is trying to match if there's any type of, or trying to measure if there's any type of violation for independence of observations, and didn't look too good just from the way that it was kind of angled. So I assume there's probably some independence of observation issues with it, which isn't too surprising. All those students are coming from one class. We're asking about study habits within a class. There's going to be some dependency among that, especially when you're talking about statistics students who have very probably similar study habits when it comes to that particular course, or any course that may be a little bit tougher. And so I'm not surprised that we see potential problems when it comes to independence of observations. All right, and then we looked at our influence diagnostics. So looking at our residuals, our studentized residuals, we identified one participant that may be influential, participant number 9. We didn't see anything with Mahalanobis distance, but however, with Cook's distance, we did identify 3 potentially influential observations. Numbers 43, 48, and number 9, which again occurred twice. So number 9 is probably going to be a concern. Probably want to make sure we deal with number 9. Then when we looked at leverage, we found another observation number 10, but it wasn't being repeated across them. And so we're not quite as concerned, because remember that just because it shows up here doesn't mean it's influential. Just because it doesn't show up doesn't mean it's not influential. Right, and so we're going to look across our evidences, and if we see a observation showing up a couple times or in multiple places, right, then we're going to remove it and then refit and see if we can improve the model assumptions, meeting the model assumptions, to get a better and more believable model when it comes to our output. So that's what we're going to pick up. We're going to do a model number 2. In this model number 2, we're going to go ahead and remove participant number 9, and we'll refit like we did on Wednesday, and just see if we can't get some improvement when it comes to the diagnostics criteria for the general linear model. All right, so I'm just going to go ahead and move our table out of the way here, get back to our original data, and just make sure that if you are doing multiple models that you are doing a save as and saving your files so you know which model you're working on. I'm not going to do that here just because I can always download a new file. But what I'm going to do is I'm going to go ahead and get rid of our participant number 9. I'm just going to right click there and clear, and that'll get rid of that particular participant. And then from here, I'm just going to refit the analysis just like we did on Wednesday. So I'll go down to analyze, then to regression, and then to linear. I'll go ahead and put in my outcome variable, so hours sleep, in the dependent variable box. Then I'll put in my predictor variables in the independent variable box. So remember, we had work hours, we had social media, we had credit hours, and we had study hours. So we'll move all those in the dependent variable box. We'll go up to our statistics, go ahead and get our confidence intervals and our descriptives. Those are all good habits to check off. We'll go ahead and click continue. Now when it comes to our plots, we do want to get a residual plot. So we're going to take our Z predicted value, and we'll put that into our outcome field. And then we're going to take the studentized residuals and put that into our X field, or our predictor field. So I'm just going to take the residuals of the model, compare it to the predicted scores on the outcome. And then we're going to go ahead and just check the histogram and normal probability plot. So that'll let us look at the residuals and see if it appears to be normal with our visual inspection. Again, we always want to look at it visually, not just with the numbers, because sometimes the numbers can be deceiving. So we'll go ahead and click OK. And then we do want to save some output here. I'm sorry, save some new variables here. So remember, we want our studentized residuals. So this will give us our studentized residuals and place it in our data view in SPSS. And we want to get our distances for Mahalanobis, for Cooks, and for Leverage. I'll click continue. And we don't need these other ones. We'll go directly to OK here and go ahead and fit the model. All right, and we'll get some output here that we'll take a look at. Now, you know there is an order of operations when it comes to looking at our diagnostics. So remember from our PowerPoint slide. So we're going to go ahead and look at the univariate analysis of the residuals. We're going to look at those residuals first. Again, we're looking for normality. We're also looking to see if the mean is close to 0, standard deviation close to 1. We want to look at the scatter plot of the residuals. Then we'll examine any other influential statistics. And then again, look at for violations and if there's any observations that we want to remove temporarily, refit, and then compare our models. So that's the order of operations that we're going to look at. So let's take a look at our output here. And I'm going to jump just to our model information first, just to see how we're doing there. And then from there, we'll look at our residuals. All right, so if we're looking at our model summary box, we see we have an R-squared value of about 0.26. It does look like in the ANOVA box that this model is significant, right? It's less than 0.05, it's 0.022. If you look at the coefficients box down here, and I look at my individual predictors, I see that when it comes to work hours, that one's really, really close to being significant. Probably close enough for me to mark as a potential predictor. And then we see that hours spent on social media predicts our sleep hours. The other two variables don't seem to, so we got credit hours and average number of study hours in a week. And so those two don't seem like they are influencing our sleep hours variable. So I'm going to go ahead and just enter that information into our comparison table just so that we have it all there. So we still have 4, again, predictors. Now we're going to say like we have 2 significant predictors. Remember, one is like 0.06 or 0.066, so it's not quite at 0.05, but it's close enough for us to be suspicious about it and consider it as a potential predictor. So I'm going to mark that there. Our R-squared value was 0.26, so we do see it looks like an improvement in the R-squared value once we got rid of that observation that was potentially influential. And then our degrees of freedom, which if we compare models we'll need later, in this case is 38. And I was 38 here because we removed one observation, so that degrees of freedom is going to decrease by 1. Now you may be tempted to say, well, model 2 is a better model because we have another predictor, and another significant predictor, and because the R-squared value is higher. But remember, that is not how we select models. The fit is more important, right? Because if the fit's not there, if we're not meeting our assumptions, then we're going to have less confidence in the model, whether it says there's 2 predictors or 3 predictors or 4 predictors or 1, it doesn't really particularly matter because it's in the confidence in the model. So if we don't have confidence, then those significant predictors could change the next time we do an analysis. And so the R-squared value is nice to look at, as well as the significant predictors, right? But it's not going to determine which model is best for us. That's where we look at our other diagnostics to help make that particular decision. So look at a little bit more of the output here, and let's see how we do when it comes to our new model here without that potential influential observation. So I'm just going to scroll down here. You notice you're going to have the histogram of the residuals. So there is a bit of a tail in the positive direction. The question is that enough to say that it's positively skewed? Maybe there's one more potential observation that we could remove that might normalize it a little bit better. But I would imagine if we removed it, then it might start to not be symmetrical the other way. And so for right now, that's pretty good. We'll look at the other statistics to determine whether or not that observation out there is a particular concern. When I look at the normal probability plot, you're going to notice here that these observations are hugging this line very, very well. This is actually an improvement from what we saw in the first model. Remember that first model had a little bit of a bubble here on the lower half of our line, our 45-degree angle here. And so this is all hugging, and this actually looks much better than what we had before. Not that it looked too bad before, but that looks pretty good. And since we're here, let's take a look at our scatter plot. Doesn't look like it's changed too much. Remember, when we're looking at that residual scatter plot, we're looking at if there's any unusual observations. Last time we identified this observation over here to the right as unusual, potentially influential, but we had another one, right? And the other one is the one that we removed. It was further out. We didn't identify this one down here at the bottom, although it is a little bit away from the other ones, but given that the stepwise nature of how these data are showing in the scatter plot, may be more indicative of what might be a normal observation if we had a higher sample size. But this one out here definitely may be a concern. Obviously, we'll look through the rest of our diagnostics and see if it stays that way. But it looks like there's one potential unusual observation in this particular output. So while we're here, let's go ahead and fill in our table for what we see. So again, unusual observations. Looks like we've decreased it by one, again, because we removed one of them that was a potential concern. We still don't have symmetry, right? So the top half of our scatter plot doesn't appear like it is matching the bottom half of our scatter plot. Part of that is due because of, you see this like kind of stepwise grading, this lining that you see here. And this is probably due to a violation of independence of observations. Sometimes you get some weird patterns when you have a violation of independence of observation. One being kind of like a stepwise, like steps on like a staircase or something like that. Those types of patterns usually indicate some sort of violation of independence. And we talked about that already, that these are all coming from the same class. We're talking about study habits. It's a tougher course because it's a statistics course. And so, the number of hours they spend and how they spend their time studying probably impacts, which would be very different from other classes, which impacts how our residuals might look. And so that may be a concern. So we don't see any symmetry there. Equal variance, again, is the spread of the values. Does the spread of the values tend to be the same going across our x-axis? And it does still look like there's some funneling. So it doesn't look like that has improved at all. So we're still going to say no there. And honestly, I wouldn't expect it to improve too much because all we did was remove an observation. We didn't really do any kind of transforms or anything. So I would still expect most of these indicators to still be no. Oh, I'm sorry. We didn't look at linearity, so let me delete that really quick. Yeah, so linearity, our biggest concern with linearity, we had that one observation like way out over here on the far right that made it look like it was curving. Without that observation, it doesn't look like that curving is as obvious. And so we do have this one unusual observation, but if you just cover that up for a second and ignore it, you'll see that there doesn't appear to be any kind of curving with the other ones, that a linear relationship between these two might be sustained, right? And so I think that has improved. I don't know necessarily I'll say that yes here. I don't think I'm going to say a no. I just might give it a question mark. But without that one observation, it isn't quite as apparent as it was before as being a nonlinear, right, not a straight line relationship that best fits those data. All right, we did look at that normal probability plot, and that actually looked better. But it looked all right before, but definitely a yes there. Let's go ahead and take a look at our residual descriptives. Check our means of 0, standard deviations of 1, and then also let's look at our student statistic with the standard error and see if that is looking any better as well. All right, so I'm going to go back to our data here. And notice again, here are those variables that we saved. We have our standardized residuals, Mulholland Novus, our Cook's distance, the leverage. So we can now look at these and see if there's any of these variables that, any of these, whether it's residual or other distance measures that may indicate potentially influential observations. So I'm just going to sort our standardized residuals. We'll start there first. All right, we'll look at our more extreme zones here in a second. But let's go ahead and get our descriptive statistics. So descriptives, frequencies. We're going to uncheck the display frequency tables box. I don't really need tables here. And then let's get our standardized residuals. Let's move them over into our variables box. Go over to statistics. We're going to want our mean and our median. We'll get our skewness statistic. We'll get the standard deviation. We'll get our minimum, our maximum, and don't forget the standard error for the mean. Again, because we want to compare our mean, which should be 0 or close to 0, to that standard error just to make sure, or 2 times that standard error just to make sure that it falls within what we consider to be no different than 0. So we'll click continue. We don't need any particular charts here because remember we already got a histogram of our residuals, so we don't need to get that. So let's go ahead and click OK, and let's take a look at our output. All right, and so it's down here at the bottom, and again, what we are looking for when it comes to our diagnostics is that we want to check to see if the mean equals 0, standard deviation equals 1, right? And then we'll check the normality when it comes to the skewness statistics. So that's really kind of our goal here. Okay, and so if I look at our mean, we get 0.000479. That's really close to 0 there. If we wanted to check compared to that standard error of the mean, if I take 2 times that standard error, right, and make it positive and negative, so 2 times 0.15 is about 0.30. So we're saying that a mean of 0 shouldn't be any less than a negative 0.3 or larger than 0.3 for us to say we meet the assumption. 0.000479 definitely falls within that range of plus and minus 0.3. So it looks like we're meeting that assumption with our mean equaling 0. Certainly no different than it. If I look at my standard deviation, we get a 1.01. So it's not exactly 1, but it is pretty close. So I don't have any concerns there. Let's move down. Let's take a look at our skewness statistic now. Our skewness statistic is 0.34. Again, for us to say that it appears the residuals are normally distributed, then we would expect that the skewness statistic will fall within 2 standard errors, right, where 95% of skewness statistics would fall in the population. So 2 times the standard error, both in positive or negative direction. And so if I have 0.36 for my standard error of the skewness, I times 2, I get 0.72. So for me to say that our residuals are normally distributed, we would expect that that skewness statistic of 0.34 would fall between negative 0.72 and positive 0.72, which it does here. And so it looks like in this particular case, we can assume a normal distribution when it comes to our residuals. So that's actually an improvement, right? We removed that one potential influential observation. We actually improve the model fit. We improve the diagnostics of the model meeting more of the assumptions. So let's go ahead and just add that to our table here. So yes, we do have a mean that is equal to 0, or at least no different. We have a standard deviation that is around 1. It was pretty close, 1.01. And now we can say that we have a normal distribution. And so we can also say yes here, right, when it comes to the descriptive statistics. All right, so we do see some improvement here. Not only are we getting potentially another significant predictor, not only are we increasing the R-squared value, right, it looks like our linearity is slightly improved, and it looks like we're meeting our normality assumption of the residuals, which is all good things. Now, the downside, or the bad thing here, of course, is that we've removed an observation as if that observation was an error or didn't exist, right? Which it did, though. And so if we don't have any real reason to think it's an error, is it correct for us to remove that observation? And that's a question that people debate quite a bit across different professors or in different labs. My position is don't throw away data because that represents a real person. As long as it's not error data, then you want to model it as best you possibly can. So we'll come back to that here in a little bit. Obviously, we'll do a transform to see if we can't retain it and still improve our model fits. So let's look at our influence diagnostics here. So again, we're going to take a look at the studentized residuals, the Mahalanobis distance, the Cook distance, and then the leverage, and see if we can't get a better numbers here, and that it doesn't look like we have as many influential observations. So let's take a look at it. So again, if you're going to look at that, we are going to go to our data view in SPSS. We already sorted our studentized residuals column. We're going to look at the most extreme studentized residual, because if that is significantly different than the rest at a greater than chance level, then we will potentially remove it or indicate that it may be influential. But if it's not, if the most extreme is not, and it falls within what we would expect to occur by chance, then there's no reason to look for any other ones. So that's why you always want to start with the most extreme. So we have negative 1.85. Let's go in the positive direction. We do have a more extreme value of 2.8 here. So that is the one that we are going to want to test first. Now we do have a formula to test that number against, so I'll pull that over really quick. So again, we're just going to do a t-test here for residuals. The subscript I tells us for the individual observation. And so our formula here, we're going to take our, which is going to be our participant for number 9. So we'll put in our most extreme residual here, and then n is the number of observations, k is the number of parameters, which includes the constant here. So if I have 4 predictors, I'm going to have 4 slopes plus the constant, which is another parameter. I'm going to put 5 there, and then we'll subtract 1 as an indicator of degrees of freedom. So if we plug in those numbers, so again, we have 2.8 here. We're going to have, I believe we had 43 observations. We had 5 parameters minus 1. Same thing in the denominator, except now we're going to subtract out 2.8 squared. And so, if you pause it, you can plug those numbers into a calculator, make sure that you get the same that I get, so that way if on an exam or in class you're asked to do it, that you're able to do it. And so the value I end up getting, once I plug in the numbers, I end up getting a value of 3.11. So 3.11. So then I want to test that value of 3.11 to the table, just like we would if we had like a t table or a z table, to see if it falls within what we consider to be acceptable or by chance, right? What we accept by what we would consider to be normal by chance. And so we have to go to our Stevens article, just like we did in class. All right, so we'll go there really quick. And then on page 338, we see our critical values for our outlier test, and this would be for our studentized residuals. So our very first column down here on the left-hand side, remember you got to turn your head kind of sideways here, but that first column going down where my cursor is our number of observations. And so we have 43, but puts us right here near the bind of the page, which is unfortunate, but you can still see it there. And then we have P prime, which is telling us the number of parameters, which is 5. And so we're going to go down that column until it intersects with our number of observations. It looks like we get a cutoff or a critical value of 3.52. So that's our cutoff, so 3.52. So if our studentized residual, excuse me, given our formula exceeds that, right, then we'll say that observation may be problematic. So in this case, it doesn't, right? So the value we calculated with our formula was 3.11, right? And that does not exceed 3.52. So in this case, it doesn't look like we have an observation that is of concern when we look at the studentized residuals. So again, if we're looking at our table, here it doesn't look like we have any, so I'm just going to leave that box blank. All right, so let's take a look at Mahalanobis distance. Again, we'll need our Stevens article for that as well. Let's go ahead and sort our Mahalanobis distance column. We'll go to the largest value that's there. Values range from 0 to infinity. And our largest value is 13.45. So again, we're going to look at our Stevens article, except now we're going to look at our critical values for the Mahalanobis distance, which is on page 342. We're still going to have the number of observations on the left-hand side. Again, we have 43, right? And then we have our, in this case, our predictors. So notice it's not a P prime, but just a P, so the number of predictors. In this case, we have 4 predictors. So if we're looking at an alpha of 0.05 or a 5% chance of a type 1 error, we go down to where it intersects with our number of observations. So right about here, and we see the cutoff is 14.96. So obviously 13 is getting close to it, but it has not exceeded it. So it looks like there's no values. The most extreme value isn't a concern, so there's no values in our data set that's a concern for Mahalanobis distance. All right, so we'll leave that one blank as well. All right, so let's go to Cook's distance. Remember, Cook's distance is relative to what is in your data set. So where do you see gaps, essentially, is what we're concerned about. So we're going to sort our Cook's distance variable. We'll scroll down, right? And as you're looking at these values, you see we got 0.02, 0.03 rounded, right? 0.03 rounded, 0.04, 0.05, sorry, we got 0.04, 0.05, 0.07, 0.07, 0.08, again rounded, 0.09, 0.11, so a slight, I don't know if that's a jump or not. I don't think it really is. It's really close to just like a 0.01 difference, and then we have a 0.11 again, and then we definitely see a jump here, right? It goes from 0.11 all the way to 0.30. So it looks like participant 48 might be a concern. So that's one that we are definitely going to mark down. Suppose you could put 35 and 43 if you're being really, really conservative. But it's clear that there's a jump between 0.11 and 0.30. All right, so I'll put that one in here. We'll put in participant 48. A slight improvement than before, because remember we had 43, 48, and 9. So it looks like only 48 is occurring across those two models, right? But within the model, it's not a particular concern, at least not yet. Okay, so lastly, let's look at our last influence diagnostic, which is going to be leverage. Remember that when it came to leverage, we had another formula to check what our critical value is going to be. So remember, it's possible influential when it comes to our outliers if that leverage is greater than 2 times P, the number of predictors, divided by N. But remember, that's conditional, right? That you will use this cutoff only when the number of observations minus the number of predictors is greater than 50. In this case, it wasn't, right? Because we had 43 minus 4 predictors gives us 39. That's less than 50. So that means we need to use this other formula. So 3 times the number of predictors divided by the number of observations. So 3 times 4 predictors is 12. 12 divided by 43 observations gives us, if you punch it in your calculator, gives us a cutoff of 0.279, or essentially 0.28. So if our leverage value is greater than 0.28, then that observation potentially could be influential and could be impacting our model results. So let's sort that last column. So again, right click, sort ascending. Go all the way down to the largest value. We see that 0.32 does exceed 0.28. If we look at the next one, is 0.23. That is within what we consider to be normal by chance. And so it looks like there's only one observation here that may potentially be a concern, and that is participant number 10. And so we'll put that back into our diagnostic table. Right? And now we have looked at the diagnostics for 2 models. And since they're all here in the table, we can compare them and see, okay, which one appears to be better. Again, given the limitations, right? We removed an observation, which is not ideal, but is the trade-off better because of that? And those are the types of decisions you have to make as a researcher. In this case, it looks like our influence diagnostics are better, right? There's no value that's shared across those diagnostics. So we do have participant number 10 and participant number 48, which may be potentially concerns, but in the reality of it, it's not in multiple places, so that it is acceptable, not best, but it is acceptable for the particular model. We meet our normality assumption by removing that one observation. Everything else looked good. Possible increase in our linearity assumption, so it might look a little bit better, right? And then overall model looks a little bit better, even though we're not going to use that as a decision. All right, so we see some improvement by removing this observation. So we got to think about, that participant number 9, was that an error? Can we somehow justify that as an error? If so, then we can remove it. But we can't just remove it and say this model is better, because that observation still may represent an actual person, right, in the population. And that one person in our sample reflecting someone in the population could be equivalent to 100 or 200 or 10,000 people in that population, right? Just depending on how big that population is. So not ideal to throw it out. So the next thing that we probably want to do is do a transform, right? Maybe we can keep participant number 9 if we transform the data to bring that observation closer to the centroid of all the other data. In the process, that may help us improve things like the positive skew, right? So retain the data while addressing and fixing the assumption violations. That would be preferred over to choosing a model that removes an observation or removes data. And so that's going to be our model number 3. We'll get to that in the next video because that gets into our next set of slides when it comes to our checking our model assumptions. Right? Transforms are going to help with that as well. So try to retain data by transforming to better meet the assumptions. So that's going to be the next video.